An object oscillates according to the formula x of t is 0.12 cosine of 12t, where all the numbers are in proper MKS units. A, what's the period? B, what is the maximum velocity of the motion? C, what is the velocity when x is 0.1 meters? And D, if this is the motion of a 0.1 kilogram mass on a spring, what is the spring constant? Although most textbooks and most instructors like to teach simple harmonic motion as an energy problem, often simple harmonic motion is simpler as a kinematics problem. What we recognize is that for simple harmonic motion to be a kinematics problem, we need to have x as a function of time, v as a function of time, acceleration as a function of time, and all the appropriate combinations in between. The standard form for x as a function of time will have an amplitude and either a sine or a cosine. In our case of the problem at hand, it's a cosine of a number times t. Now what we recognize is that there's no such thing as the sine, cosine, tangent, or any other trigonometric function of a number whose units are time. You can't take the sine of 2 weeks and you can't take the cosine of 3 months. Instead, one requires a unit conversion, and this unit conversion becomes the fundamental constant of any oscillating motion. We call it omega, and the reason is that the proper argument of cosine is radians, and we need to multiply by t, so omega will have the units radians per second, which is reminiscent of the angular velocity that we had earlier in the class. We recognize that omega itself, as a unit conversion, must be something that is the equivalent of 1, and so the numerator should equal the denominator. We wish to have a numerator of radians, a denominator of seconds, and so therefore omega itself is 2 pi radians over tau seconds, where tau represents the period. Similarly, since we recognize that 1 over the period is the frequency, omega can also be written as 2 pi times the frequency, still in the units of radians per second. I like to refer to omega, the period, and the frequency as synonymous variables. The equal sign here is not simply that nature decided to make these equal, but the equal sign represents the fact that omega, the period, and the frequency all encode the same information about the oscillation. Therefore, given any one of these, you know all the others instantly. The one that is most natural to the system is omega, and that's why this is the one we keep in most of our equations. However, you may be asked for period, in which case find omega, and then use this equation. You may be asked for frequency, in which case find omega and use this equation. Or you might be given period or frequency, and your first step should be to convert this to an omega. We can take a couple of simple derivatives of the previous formula to come up with the velocity and acceleration terms. Taking a derivative of this position expression, we will find that the derivative of cosine is negative sine, and we'll pull out a factor of omega in the process. Another derivative yields the acceleration as a function of time. This is not constant acceleration motion, and so acceleration does vary. In this case, we will retain the minus sign and the amplitude, pull out a second factor of omega, and retrieve a cosine dependence of omega t. To get a complete set of all possible pairwise equations, we need to eliminate t from certain combinations. For example, if we wish to find the velocity position equation, we need to take the velocity time equation and the position time equation and eliminate t. You'll see that that appears to be rather difficult at first sight because one of these contains sine and the other one contains cosine. However, what we recognize very cleverly is that x divided by its maximum value, which is the amplitude a, is cosine. V divided by its maximum value, which is a times omega, is sine. And a favorite trigonometric identity is that cosine squared plus sine squared is equal to 1. That means this relationship will give us position at any velocity. Similarly, we can combine velocity with acceleration by dividing each of these by their maximum. Velocity over its maximum value of a omega squared plus acceleration over its maximum, which is a omega squared, quantity squared, reads sine squared plus cosine squared, and trigonometrically this is always 1. Finally, the simplest one is to get x as a function of acceleration, and in that case we see that since x is amplitude times cosine, and acceleration contains amplitude times cosine, we get a very simple relation that acceleration is negative omega squared times x. This completes all possible pairwise combinations of the dynamic variables for simple harmonic motion, and we'll be able to solve simple harmonic motion problems the same way we did with kinematics, by selecting the appropriate equation to answer the question at hand. It's worth collecting in a small table some of the things we mentioned during the process, and that is that x has a maximum value, which is equal to the amplitude a. V has a maximum value equal to the amplitude a times the angular frequency omega, and the acceleration has a maximum value equal to the amplitude times the square of the angular frequency. These relationships will be extremely useful as we solve various problems. Finally, we haven't said simple harmonic motion of what? We have simply said that some object is in simple harmonic motion. The details of which object and under what circumstances you get simple harmonic motion are entirely encoded into the variable omega. And we can make a brief table summarizing a few of the common situations. If we have a mass oscillating on a spring, then the omega is square root of the spring constant k divided by m of the mass. If, on the other hand, we have a simple pendulum, then the omega is the square root of g divided by the length of the pendulum L. And finally, if we have a physical pendulum, which is an object of some moment of inertia oscillating around some point, then in this case the omega is the square root of mg times d, the distance between the center of mass of the object and the pivot point, divided by the moment of inertia of the object around the pivot point at hand. So, all simple harmonic motion problems will involve manipulations of equations involving omega, and the omega itself will depend upon the physical constants involved in the system. Let's take a look at the problem at hand, and we'll find that now it solves very easily. Part A asks us, given the formula above, what is the period of the motion? Well, looking at the formula, we recognize the form. The coefficient in front of the cosine is the amplitude A. So A will be 0.12. And since this is MKS units, that should be meters. And the coefficient in front of T must be the omega of the motion, so that we have the omega is 12, and in MKS units, this should be radians per second. The variable period asked for in Part A is the synonymous variable to omega. Since omega is always equal to 2 pi divided by the period, we find immediately that the period is equal to 2 pi divided by omega, which gives us the result pi over 6, or 0.524 seconds. In Part B, we are asked for the maximum velocity of this motion. We recognize that always in simple harmonic motion, the maximum value of the velocity will be the amplitude times the omega. Since we have the amplitude of 0.12 and the omega of 12, we plug those in to immediately find 1.44 meters per second as the maximum velocity of the oscillating object. Next, we're asked for the velocity when x is 0.1 meters. Let's formulate this as a well-formed question. To satisfy the question, we must provide a value for the velocity v. This is an ill-formed question. Because v takes many values, it oscillates back and forth between plus and minus a omega. To make an explicit question, we would like to find the v when the x was 0.1 meters. In order to answer this, we'd like to have a relationship between the velocity and the position. And in the previous discussion, we derived this relationship that x divided by its maximum squared plus the velocity divided by its maximum squared must be equal to 1. So in this case, we simply need to plug in an x of 0.1 and all the rest of the information that we know quite well to solve for the velocity itself. Since we've already noted that the maximum x position is 0.12 and we calculated the maximum velocity to be 1.44, the only unknown in this equation is v, and v turns out to be 0.796 meter per second, below the maximum velocity as it must be. Finally, and only in part D of this problem, do we actually describe what the physical situation is governed by our equation x of t. Part D says if this is the motion of a 0.1 kilogram mass on a spring, what is the spring constant? When we decide what is the physical kind of motion, we are referencing the value of omega. And we recognize that for a mass on a spring, the omega will be equal to the square root of the spring constant divided by the mass. Since we've already decided that the omega of our system is 12, and we've been given that the mass is 0.1, the only unknown in this equation is the spring constant k, and so we get the result 14.4 newtons per meter.